talk.
Thank you, Penny. So it's my pleasure to introduce Professor Ed Stolper from the California Institute of Technology, who has kindly accepted the invitation to present for today's school seminar, as well as tomorrow at 12:30 for the Petrology and Geochemistry group meeting, to which everyone is welcome and encouraged to attend. For most of his career, Ed has adopted a multifaceted approach to research. Although principally concerned with igneous processes, Ed's diverse use of theoretical, experimental, field-based and computational approaches to his research has resulted in an extremely rich and productive career. For over 40 years, Ed has studied igneous rocks from the Earth, Moon, Mars, and meteorites from across the solar system. He has contributed tremendously to the understanding of the processes by which planetary interiors melt, the role that various volatiles such as water, carbon dioxide, sulfur play in igneous processes, and the oxidation state of magmas and the Earth's interior. He has published key papers on the petrogenesis of meteorites, terrestrial basalts, island arc volcanics, and Martian meteorites and rocks. Ed's recent research has focused on the chemical zonation in melt inclusions in olivine, plagioclase, and pyroxene, and experiments and modeling to determine cooling histories, the thermal histories of tektite impact gases, as well as the influence of phase equilibria and peridotites on the oxygen fugacity of the upper mantle, which will form the basis for today's talk. Ed's contribution to the earth sciences has been recognised through numerous awards and memberships into learned societies, of which include the recipient of the 1997 Arthur Holmes Medal, the recipient of the 2004 Arthur Day Medal, the recipient of the 2012 Victor Goldsmith Medal, recipient of the 2017 Roebling Medal, and in 2019 he was the recipient of the Geological Society's top honour, the Wollaston Medal. So Ed, thank you a lot for accepting the invitation to talk today. If you're all good to go, I'll pass it over to you.
Okay, thank you very much. There was one not quite correct statement in your introduction. It has to do with this talk. I haven't done much on FO2. This is it, actually. And then I had a postdoc who was using Zanes to measure FO2 as a function of degassing. But the origin of this is a one-shot, a one-off deal, is I did not understand why and how FO2 would vary in the mantle. And I was so frustrated that I didn't understand it that I got together with Ollie Shortle, principally, and did what I'm going to talk about today. And I might do a little more, but I'm not well known for this. And in fact, there are people at ANU who are well known for this, and it's one of the reasons I'm enthusiastic about hearing what they have to say. So the title is The Effects of Solid-Solid Phase Equilibria and Partial Melting on the Oxygen Fugacity of the Upper Mantle. You know, I have a feeling I won't get to the partial melting part. It's pretty short and it's very simple, but if I'll just drop it off, I don't get to it. One thing I did want to say, in addition, we talked about this before as people were probably assembling. I would love it if people have questions during the talk. I not only don't mind being interrupted, I think it helps people understand what's going on. And so if you have a question, the way we worked it out was that you put it in the chat. You don't say the question, just say, I have a question. And then Zach will wave his arms to do something to get my attention. He's right up there next to my picture and I ought to see it. And then the person can go ahead. Okay? So if there are no questions, that's fine. But I don't want people to feel, oh God, you know, I don't want to erupt and it messes up the sound and I'll wait till the end. Because sometimes when you wait till the end, the question no longer is useful. And yet it would have been extremely useful earlier on. Okay. How do I make this? No, I'm not able to make go forward. Maybe press the wrong button. Okay, there we go. This is, okay, so the problem is I don't see the upper part of it. The first thing I want to do, and I mentioned that I'd given this talk twice before, about a year and a half ago. And I've come to the conclusion that outside of the people outside of petrologists perhaps, and even petrologists have some trouble with what FO2 is. So I better start with a definition of it, so that everybody's comfortable with it. I'm wondering if I can change this. I'm not seeing my whole, there we go. So let's define it. So let's start with the definition of the chemical potential of oxygen. And this is a very simple definition. It's not the only one. The chemical potential of oxygen is if I have a material, I can't see myself now, wait a second. If I have a material and it has a certain Gibbs free energy. And then what I do with constant temperature and pressure, I titrate in an infinitesimal amount of oxygen, or I take it out. And then I look how much the Gibbs free energy changed with that change in the amount of oxygen in the system. You say, well, who cares about this? Well, the reason we care about it is that, as presumably everybody knows, when you have a system at equilibrium, all the phases have the same pressure and temperature and chemical potential of every component. And so when two phases are in equilibrium, they have the same chemical potential of oxygen. When one has a higher chemical potential of oxygen than the other, then oxygen, maybe not O2, but something stoichiometrically adding up to oxygen, will flow from the one with high chemical potential to the one with low chemical potential until they're the same, and then they're in equilibrium. So how does oxygen fugacity fit into this? Well, a guy named Lewis, who was a famous Berkeley chemist around 1900, he invented the fugacity. And so we have our chemical potential of oxygen. Well, it's then equal to a standard state of oxygen, only dependent on temperature, plus RT log FO2. And that, plus the next line, which is required, is the definition of fugacity of oxygen. So it's a functional form. And the next line, by the way, is that this is what the FO2 is, but in the limit of the total pressure going to low enough so that it's at, it's like an ideal gas, it's close to an ideal gas, and actually we take the limit as P equals 0, you could make it 1, that the FO2 is equal to the PO2, the partial pressure of oxygen. And the reason this functional form is chosen is because it's the same as that of the ideal gas. So when Lewis wanted to deal with non-ideal gases, he said, let's have something that in the limit of low pressure, that it looks the same as what we know it has to look like. So the point is that people will talk about FO2, but what they're really doing is relating it, it's a shorthand for the chemical potential of oxygen, and that oxygen will flow between materials in response to a difference in chemical potential of oxygen. Another aspect, so that people are not scared away by this, you know, whenever you're dealing with volcanology, maybe not if you're dealing with kimberlites, but for most volcanology, the pressure is so low that FO2 is equal to PO2. And if you said the partial pressure of oxygen, everybody would understand you. If you say fugacity of oxygen, people who are not deeply into this kind of thing don't really understand you. So that's what it is. It is a proxy of the chemical potential, which is something which has to be the same between phases when they're in equilibrium. When something has a high chemical potential or a high oxygen fugacity relative to something else, oxygen will flow from the high to the low. Okay, so I want to get that out of the way. So I can't read what's at the top of my thing, but it's basically why there's long been an interest in the FO2 of magmas and the mantle from which they're derived. And this is for a variety of reasons. One is that if you look at variations in FO2, and we'll see that in a few minutes in magmas and in the mantle, you can set constraints on the processes that have generated the variations in FO2. And that could be metasomatism. If we're in the mantle, it could be metasomatism, mixing in of subductive material. It could be partial melting. It could be flow of fluids, which I guess is metasomatism. And so these are all processes we know go on in the mantle, but they will have an imprint on FO2. Also, FO2 has an effect on petrogenesis. By the way, in the first line, in magmas, crystallization, if you crystallize olivine, you will enrich the melt in Fe3 plus relative to Fe2 plus. So crystallization of olivine or pyroxene affects the FO2. Degassing, particularly the sulfur around, you can generate very large variations in the FO2 of the residual magma due to degassing. Now, if the second bullet, if I have something that has a very high FO2, if it's a melt at a high FO2, it will crystallize differently, and the liquid line descent will vary. If I have a mantle that's very oxidized versus one that's more reduced and therefore has a different FO2, the characteristics of partial melting will vary. The characteristics of the melts that are generated will vary. And finally, and one that's of great interest, and why a lot of people seem to be working on this problem, is the large-scale planetary issue of the feedback between the mantle and the Earth's surface and atmosphere, and the influence on recycling. And let me give you two examples. There are people who believe that the great oxidation event of the Earth's surface, the atmosphere before the ocean, at 2.4, 2.5 billion years, was influenced by the FO2 and the change in the pressure of eruption, in the change of the source, that the gases coming out due to varied their FO2 and therefore influence the change in the oxygen content, the oxygen partial pressure of the atmosphere. Likewise, if you take material that's been exposed to the oxidized atmosphere and you subduct it, it has an influence on the interior. People have long believed, or some people have believed, that the higher FO2 of subduction zone of material that's subducted then makes its way into the upper mantle or melts directly into the mantle wedge or melts directly. And that higher FO2 in the mantle is changing what's going on, and those variations are important. Also, so that there's both the progressive oxidation of the mantle, if that occurs, or the local oxidation of the mantle, if that occurs, and also the feedback between that and the atmosphere. So this is why people are interested. Now, there's been a real uptick in the interest in this because the way in which you interrogate a rock or a magma for the FO2 or the chemical potential oxygen that it records is by looking at the ratios of heterovalent elements. So the Fe3+2+ ratio, or the europium 2+3+ ratio, or the sulfate to sulfide ratio. And until recently, it was hard to measure these things on a scale that was sufficiently interesting to be able to address any individual rock. But with the more widespread availability of Zane's and Mott's power spectroscopy, you can measure the ratios of these heterovalent elements in melt inclusions, in small bits of glass, in minerals more readily. And so there's an explosion of information on the ratios of these elements and therefore FO2s and how they're varying in one rock to another, one magma to another. Now, what I'm going to take advantage of today is progressive, and it's always improving, but improving and improved thermodynamic models and databases make it possible to model the effects of pressure, temperature, degassing, phase chemistry on FO2 and vice versa. So what I'm going to show you today is largely a modeling effort. In fact, it's probably a little bit of thinking effort to understand what the models are telling us, but it's a modeling effort. So these two things together, I think, have really made FO2 a much more popular topic. A lot of people work on it now. So let's get a sense of the variation, and the quantitative aspects of this will vary. This is from Ian Carmichael in 1991, and Ian loved FO2, and the reason Ian loved FO2 is he liked doing wet chemistry, and he to relax on a Saturday, he would measure Fe3+2+ ratios of glasses and minerals and rocks, and so he was measuring a lot of Fe3+2+ ratios. And here is a histogram from his time, and it hasn't changed all that much. We'll see in a little bit that the absolute value of FO2 is not terribly informative. What you want to do is see variations in it, and you usually look at the FO2 as defined previously from the chemical potential, and you take the log of FO2 and you subtract from it the log of the FO2 of a mineral buffer. And this is nickel-nickel oxide. We'll get into what these buffers are a little bit later. And what you can see is that, so this is 0. So this would be an FO2 that's equivalent to that of the nickel-nickel oxide buffer at 1 atmosphere, probably 1200 degrees. And these are Morbs. These are Hawaii, representative ocean island. Here is a range of typical island arc lavas. Maybe they have some continental arc ones, I don't know. And then here, because Ian Carmichael worked on them, are these bizarro lamproites, actually lampropheres, not lamproites, and I want to sell lamproites when we talk in Australia, but lamproferes, very alkaline things that he was studying in Mexico. And what you can see is there's an 8 order of magnitude range in FO2 among these magmas. This is a big range in any parameter, like a news story. So it's interesting and it's big, and interest in the processes that produce these variations is great because it's so big, and it is information on petrogenesis and provides information on evolution of the rocks after they're generated by melting. Okay. And then here's this was a little hard to do because there's a lot of data and some is not very good. But here is from Miller, who has the same model that I'm going to talk about, a very robust thermochemical model for dealing with peridotite calculating FO2 based on measurements of Fe3 plus 2 plus in either pyroxenes and or garnets and or spinel, and calculating FO2. And we see again a range, not as big, but 4 orders of magnitude variation in FO2. So there are variations, and the issue is what causes them. And some of them are already alluded to. One is that variation that we see there is inherited from the sources. There are some sources, those are the lanthropheres, that are have a very high chemical potential of oxygen and basically have a high Fe3 plus 2 plus ratio. And there are some, like the morbs, that are much lower in their Fe3 plus 2 plus ratios, and that these are inherited from sources that had low Fe3 plus 2 plus ratios in the case of the morbs, and high Fe3 plus 2 plus ratios in the case of those lanthropheres. And island arcs were intermediate, but they were 3 orders of magnitude more oxidizing than the morbs, and that surely is related. Some people disagree, but most people would accept that that's related to the effect of subduction, the oxidizing material. There's also processes, as I said before, of acting on mantle-derived melts, such as crystallization. And it's crystallization of a spinel or iron titanium oxide. It tends to make it more reduced. Crystallization of olivine tends to make it more oxidized, but that can do it. And also degassing has a really big potential effect if it's a sulfur-bearing gas. But the third one is the one I'm going to focus on. And it's people are aware of it, but I'm going to try to go through it systematically for the upper mantle. And that is variations in FO2 in a peridotite as a result of reactions among phases, heterogeneous phase equilibria in the peridotites, in the absence of any variation in Fe3 plus 2 plus ratio of the rock. So we're going to talk about a mantle rock that is constant bulk composition, including oxygen. And as we move it through pressure temperature space, how does the FO2 change? And we'll see it changes, not by 8 orders of magnitude, but it changes by 2, up to 2, from up to 40 kilobars or so. So in the upper mantle. Okay. So what did we do? What we did was, first of all, assume a single peridotite composition. And a little bit more later, we'll see on some other compositions. But we just took a representative estimate of the depleted upper mantle reservoir, DMM for depleted. I don't know what one of them is mantle. I don't know what the second M is. Model. Maybe. It has about 3% of its iron is Fe3 plus, and 8% iron. And we're going to make the assumption, and this is a critical assumption, that iron is the only multivalent element. We're not putting sulfur in. We haven't put carbon in. It can go anywhere from carbon 0 up to +4. We assume them, and then we choose 2 independent thermodynamic models. One of them is melts. Again, it's derivative from Ian Carmichael, who I mentioned before, but Giorso is his student that has really made a great career of making this available. And the second is Perple X model, which is based on Holland and Powell's thermochemical database. And there's implementation of it, and we're using the version of the model in Jennings and Holland 2015. And we use Perple X to implement it. It's a calculational scheme, it's not terribly important. And what we do is for this DMM composition, we calculate the stable phase relationships of this peridotite composition from 1 atmosphere to 40 kilobars and 1,000 to 1,600 centigrade. And this gives us, and it's done by Gibbs free energy minimization. You find the minimum Gibbs free energy, and that gives you the phase abundances, their compositions, including the Fe3 plus over Fe total in each phase, and it gives you the chemical potential of oxygen from which the FO2 can be calculated. Now, there are other models out there. These are 2 that are widely used, however, and they have their own strengths and weaknesses. They have different approximations, and we'll see that some of the differences there's a lot of stuff that's in common, which suggests it's not an artifact of that particular model. Now, it could be that all the models are wrong, but these 2 give similar results on some very fundamental things, and on some things they differ, and it's pretty easy to understand why they differ and what it means. So that's what we're going to do. First of all, I added this, as I said, I gave this talk twice before, and I decided I had to add this because for some reason, I got some questions after the talk, not during the talk, after the people just talking to me, which clearly made it clear they didn't quite understand what I was talking about. I'd like not to happen today. So again, ask questions if you don't get it. So let's just take the following reaction among major peridotite phases. So phaolite plus oxygen goes to ferrocylite plus spinel. Forget about the coefficients, although they wind up being a little important later, but not for what we're doing. So if we have olivine, OPX, or CPX, let's just say OPX, olivine, OPX plus spinel, and we measure, let's start with it being just pure phaolite, ferrocylite, and magnetite. We can write an equilibrium constant for this reaction, and that's K, the function of pressure and temperature, and it's got the activity of the products, the activity of ferrocylite and the pyroxene cubed because of this, times the activity of magnetite and the spinel squared over the activity of phaolite and the olivine to the 6th power times times FO2. And if the phases are pure, that is a pure phaolite, ferrocylite, and magnetite, then the activities are 1, and then K is just equal to 1 over FO2. Okay, so that's the notion of a buffer. So although ferrocylite is going to be metastable under low pressure, if you have phaolite, ferrocylite, and magnetite, it fixes the FO2 at a particular pressure and temperature. That just is what this says. Okay, but now if I vary pressure, we know that the partial derivative of K with respect to P at constant temperature is the volume change of this reaction minus the volume change of the solids in the reaction over RT. And so that means the volume of this plus the volume, 3 moles of the volume of 3 moles of ferrocylite plus 2 moles of magnetite minus the volume of 6 moles of phaolite. Since there's extra oxygen over here, this side has a higher volume than this. And so delta V is positive, but the whole thing is negative. So as we increase pressure, K goes down. Okay. In order for K to go down, if we have pure phaolite, ferrocylite, magnetite, the FO2 has to go up. So if we squeeze on an assemblage of phaolite, ferrocylite, and magnetite, the FO2 has to go up. So that's a simple explanation of why at constant pressure, with varying pressure and temperature, and with no funny business and activities, nothing but olivine, pyroxene, and spinel, you will get variations in FO2. Right? And that, you may think I need to worry about the changes in Fe3 plus 2 plus of the rock, phase proportions. They don't matter. If I have this buffer, the FO2 will go up in this very simple way with no change in Fe3 plus 2 plus, or with a change in Fe3 plus 2 plus in the rock. Okay, so I just did all of that. Temperature does the same thing, but it has the enthalpy instead of the volume changes, will also result in changes in FO2. What else can change? So we're going to be doing these calculations on a system at constant bulk composition where we vary pressure and temperature. So that K can vary, and that you can see why you would get changes in FO2 with pressure and temperature. But there are several other reasons why the FO2, and they're related, will change with pressure and temperature. So even if, suppose it's no longer pure phaolite, ferrocylite, magnetite, but they're solid solutions. So it's Fo 90, ancetite 91, and 5% magnetite in the spinel. So each phase has a composition, and each phase has, but we don't care about, it's not just the composition, we need to know the activities have to obey this. But as I change pressure and temperature, the activity coefficient times the mole fraction is the activity, the activity coefficients change with pressure and temperature. So if I conspire to keep the olivine, pyroxene, and spinel the same composition and just increase pressure or change temperature, FO2 will change because the activity coefficients will change. But also, it's hard to conspire to keep them constant in composition. If I change pressure and temperature, the composition of the olivine, the pyroxene, and the spinel will change, and that will lead to changes in the activity, which then the product of the activities over FO2 has got to be equal to this constant. And so therefore, the FO2 responds to these changes in activity and leads to changes in FO2 with pressure and temperature. And the last one is what we're going to focus on, is that you can get big changes in the compositions of these phases, the olivine, pyroxene, and spinel, for this particular example. If you have phase changes, like olivine plus plagioclase going to spinel plus pyroxenes, the change from a plagioclase to a spinel lherzolite, or spinel lherzolite to a garnet lherzolite, you can, these phases that are outside of this particular equation can lead to changes in the composition of these phases, which will then affect the FO2. So I hope everybody gets that, because that's what we're going to be talking about. Okay, so here's the result of the first calculation. So this is simply, on the left is P melts, on the right is Perple X. We're plotting temperature versus pressure, and it's contoured in FO2, going the blues like minus 10 bars, and 10 to the minus 10. And up here, we're up at 10 to the minus 4, 4.5. So one thing you can see is is that there's a big range in FO2 as you change pressure and temperature. This is 6 or 7 orders of magnitude from the lower left of this to up here, all right? And so there are big changes. Another thing to see is that the two calculations have very similar overall features. Now, the boundary between the blue-yellow and the blue-yellow, it's at a different height, okay? You can see that this here is higher than this here. But the shapes and the overall behavior are similar. So these two models are capturing a very similar thing. But the other thing to notice is the control that these boundaries, so this is plagioclase lherzolite, the small label for which I apologize, spinel lherzolite in this field, and garnet lherzolite over here. And you see kinks at the spinel out, garnet in boundary here when you go from spinel to garnet lherzolite, and kinks from the plage to the spinel lherzolite. This we're going to focus on. Okay, so this is just raw FO2, and this is reflecting, although there's a lot of reactions going on here, something comparable to this reaction. You know, you can write out probably 9 or 10 important reactions that interact with each other among the components of the various phases, and they all have to be satisfied simultaneously. But overall, it's this effect that as you go up pressure, the K goes down, and these things don't change that much, although they do change, and FO2 therefore goes up, and that's why you see an overall increase from here over to here. Okay, so now let's take a slice, just a constant, an isothermal slice, all right? And we don't have to look at both of them. We'll just look at this one. We'll look at the Perple X calculation, since they have similar behaviors. So here are the number of things here. This is just log FO2, absolute log FO2 versus pressure up to 40 kilobars. Here then is just what our raw FO2 is doing. It goes down in the plagioclase lherzolite field. It goes up, back up a little bit in the spinel lherzolite field. It's a big jump, and then goes up a lot as you go across the garnet field. In the P-melts one, it does similar. There are different levels. You can see that this is a difference between them, but the overall behavior is similar. It goes down, and then up a lot. Doesn't change much in the spinel lherzolite field. Now, people don't like to look, and for good reason, don't like to look at the raw FO2. They want to take out as much variation as they can to leave only what's important left behind. And so what they usually do, we looked at a buffer for phaolite, ferrocilite plus magnetite. The more common buffer that everybody uses is phaolite, magnetite, quartz. So the reaction phaolite plus oxygen goes to magnetite plus quartz. And just as the FO2 went up as you went up pressure for phaolite, ferrocilite, and magnetite, this is that variation in FO2 just due to the change in K. All right, the phases are all constant in composition, phaolite, magnetite, and quartz. And so you get 9.5 up to, say, 6.5, 3 orders of magnitude variation just from the change in K. So what people like to do is they normalize. They take, let's take this, here the FO2 of the raw FO2 minus that of a buffer. And as I say, people like to use QFM. And the idea, you see the overall trend of the black is sort of parallel to the FMQ, and this is sort of true. And even though they're not the same phase assemblage, because one has quartz in it and one doesn't, that's why it's considered to be a reasonable thing to use for normalizing, because it takes out the average slope. And then what you're left behind with, when you subtract the solid one from the dashed buffer, you're left with the red. Notice the scale is different. So we've reduced our variation from 10 to the minus 10 to 10 to the minus 8. is now varying by about 1 order of magnitude overall when we do it relative to QFM. So this is what people usually report when they think about in life. There are artifacts associated with it, which I may get into, but I may not. But this is what they like to use. I would tell you in particular, we're going to see that this hump is an artifact, because what we're interested in is this behavior of the actual FO2, and it's varying in a particular way. We subtract out this and we're left with a hump, and you shouldn't have it there. And we'll see why the hump is misleading. Okay, so that's what we're going to do. We're now going to, the one before, we had raw FO2 contoured. Now we're going to contour delta QFM, the difference in the log of the FO2 of the output of our model and the log of the FO2 of the quartz phthalate magnetite buffer. And now it's gotten simpler. First of all, the range has changed. Instead of being, what did I say, 6 or 7 orders of magnitude, it's done its job. It's got us down to 2 to 3.5 orders of magnitude variability. And now the control, let's look at this one. The control of these phase boundaries between plagioclase, spinel, lherzolite, spinel, and garnet lherzolite really becomes apparent, all right? That's the dominant effect here. You go down in delta QFM until you hit the spinel field, then you don't change very much, and then you go up to the maximum here, but you go up overall. And by the way, one thing I forgot to say, and I wish somebody had asked about this, is we're doing one other thing. It was in the label, but I dropped it off. In all of this, one of the things you can do with these calculations is you can do numerical experiments. And what I've chosen to do here is, if we look, the MELTS model calculates, this is where the solid is the peridotite. Perple X calculates, this is where the solid is the peridotite is. But I've made the rule, we are not going to allow liquid to be present. I don't care about the effects of liquid. I'm interested in what happens among the solids. At the end of the talk, I'm going to talk, I don't use up too much time, I'm going to talk about the melt part of it. But so all of these down here are stable assemblages, because melt shouldn't be present, but everything up here is metastable. Liquid should be present, but we have denied it stability in these calculations, right? So now we get to look at the trends over a larger pressure and temperature of the liquid absent reaction. So it's all stable down here, metastable up here, same here. And now we get to see quite clearly the behavior of this, and the normalization really helps, right? And this is the major result we're going to try to deal with and understand. The major result is that there is there's a low point in the FO2. The blues are the low FO2s relative to QFM in the spinel field relative to both plagioclase and garnet. Let's skip that and go on to this one. So now we've invented, in order to even make it clearer, because QFM is sort of arbitrary, it doesn't look quite the same if you use that phthalate ferrosolite magnetite, or if you use nickel oxide. There's lots of buffers to use. It's sort of arbitrary, and you get slightly different looks. But what we're interested in is, it's clear that plagioclase and garnet and spinel are playing big roles in this. So we would like to know how the peridotite would vary with pressure and temperature in FO2 if we didn't allow plagioclase, spinel, and garnet to be present. So rather than normalizing to FMQ, let's normalize to the peridotite itself, where we have forced it to be an assemblage of olivine, OPX plus clinopyroxene. Melts has to include spinel. So it's olivine, orthopyroxene, clinopyroxene, plus or minus spinel. And you can see that here. So here's the variation in the FO2. If we calculate in Perple X the FO2 variation of the same bulk composition with pressure at 1100, where all the aluminum is dissolved in the pyroxene, that's basically what's happening, all right? That aluminum wants to go into the plagioclase, it wants to go into the spinel, it wants to go into the garnet, but we're saying, sorry, you can't go there. Let's do a metastable assemblage of the same composition where those phases are not allowed to form, and use that as our normalization. So now, instead of subtracting the FMQ from our black, we're going to subtract the green from our black. This one is in melts. This one does not have spinel. It's olivine, orthopyroxene, clinopyroxene. This one, just because we have chromium in it and melts, requires chromium. If you have chromium, you have to have spinel. So therefore, it's exactly on the calculations of the spinel field, which is olivine, OPX, kind of pyroxene, so spinel. So now the next thing is the same figure where we have now normalized to itself at where garnet and spinel, garnet, plagioclase, and possibly spinel has been suppressed. Spinel is not suppressed here, but it is suppressed here. Now it's really plain. You know, here's our boundary between plagioclase and garnet, spinel, lherzolite. Here's our boundary between garnet and spinel. And these things are very well organized. The FO2 isopleths, the contours of constant FO2 are clearly related to these boundaries. Okay. So the pattern is simplified, and now we've extracted, we haven't got an explanation for it yet, by the way, that the FO2 is varying somehow along with these major luminous phase transitions, which is how we think about what's going on in the upper mantle. So here then are these, go back to here, go back to here, we're now plotting the difference between the black and the green curves. Okay, and here's P-melts, here's Perple X. You know, they really look so similar. Now, once we've done this kind of normalization, we can see there's a very simple pattern. A big decrease in FO2 continuously across the plagioclase lherzolite field. Not much going on across the spinel lherzolite field. There can't be anything going on in this one because we've got, it's absolutely at zero because the normalizing assemblage is the same as equilibrium assemblage. And then you get this big jump here. You don't get it here. Here it's just a smooth increase. Big jump. And I'm not going to say much about this big jump. I'll say something a little later, but it's related to the spinel out reaction. And then a more gradual increase with a hump. And now you notice a real difference between the two models. In the melts, P-melts, as you cross the spinel from the garnet lherzolite field, you go up continuously with a concave down. It goes up a lot at first and then less. This has this steep thing here, but then it goes up and it has a maximum. This difference is related to a key difference between P-melts and Perple X. Melts does not put any Fe3 plus into the garnet, whereas Perple X does. And this hump is due to the presence of Fe3 plus in the garnet, which is important. Okay, and so we're looking at variations about 1.5 orders of magnitude. Now, out of our 8 orders of magnitude variation on that Carmichael figure, it doesn't seem like much. But when we're looking at the variation across all of Morbs or the dominant variation across island arcs or the variation in OIBs, these numbers are comparable to the variations that you have. So now we're going to do another class of experiment, that a numerical experiment. On the right is just the overall thing. Now we're going to use Perple X, and we're going to turn plagioclase and garnet and spinel off and on. So if we look at what our assemblage of olivine orthopyroxene, our metastable olivine orthopyroxene plus clinopyroxene assemblage does, relative to itself, it's just 0. No variation in FO2 because it's, 1 minus 1, 0. Now let's turn on spinel. Allow spinel to be stabilized, but that's the only luminous phase or highly luminous phase. Obviously, the pyroxenes are luminous because they're containing all the aluminum in the metastable assemblage. Turn on the only highly luminous phase, and it varies. It changes a little, maybe 1/10 of a log unit, but there's just not that much spinel. And you might think spinel ought to control what's going on because it's an Fe3 plus bearing phase, got magnetite in it, but there's just a small amount of it. So it's not dominating what's going on. Now let's turn on plagioclase. So here it is when I don't have any plagioclase. If I turn on plagioclase, the FO2 jumps up, okay? And it jumps up by more at 1 atmosphere. It just goes down continuously. The increase when I spontaneously change from my metastable to my stable assemblage is an increase in FO2, but the amount of increase goes down and actually is gone when you get to the spinel edge of the field. So turning plagioclase on and off is critical to this variation. If we then keep going up in pressure and we don't allow, I don't know why I keep doing that, I don't allow garnet to form, it just happily goes along without changing any FO2 because now if the plagioclase is all gone, and up here, the normalizing assemblage is just olivine, orthopyroxene, and clinopyroxene, and that's what the assemblage is allowed. Now let's turn garnet on. So down here, there's no plagioclase, so we move along, increasing the pressure. the FO2 is changing because the FO2 of an olivine orthopyroxene, clinopyroxene assemblage is varying, but we have subtracted that out. As soon as you reach the garnet in transition, but this is the garnet in transition without spinel, we then get an increase in, it goes up and then reaches the maximum and then comes down. So it's quite clear that the FO2 is not just that this FO2 variation doesn't occur if we don't have the phase reaction, the phase changes in plagioclase, spinel, and garnet. Those are what is causing it. Okay? How is it causing it? Now, early on, I noticed that, you know, it could have, and as I say down here, it could be just, I say it someplace. It may just be a coincidence. It isn't, as it turns out, but for a while I thought maybe it was. And that is the shape of the isoplex in constant FO2 reminded me of the shape of the alumina isoplex in the pyroxene and peridotite. So what these are is this is a contour of constant aluminum in orthopyroxene. Could be clinopyroxene too, but this happens to be orthopyroxene. Constant, the amount of aluminum remains constant as I go down in increased pressure, decreased temperature. And then across the spinel field is constant, and then it goes up again. And these shapes are very similar. The behavior is actually opposite, but we'll see in a moment that they track each other perfectly. As we go up, let's go up along here, increased pressure, FO2 is high, low, low, lowest. Here, the alumina content of the pyroxene is low, and it goes up, it remains constant, and then goes down. But the isoplex look a lot like it. And so, and that this works quantitatively. Now we've taken these models, and this is one of the things you can do in these models, is you can calculate any activity that you wish. And so here, they're both the same, so we'll just use this one. The alumina activity goes down, which will increase pressure. This is at 1300, not 1100. Within the spinel field, it remains constant, and then it goes up. The activity of Fe, which one did I get it right? The activity, I just did Fe2 here. The alumina activity goes up, goes across, and then goes down. The activity of Fe2O3 in the pyroxene goes down, and it goes up. So they're absolutely, they're negatively correlated almost perfectly. And again, this may not be causal, but we'll find out that it is. And this is just, I'm not just going to explain it in words. To me, it's very simple. It may not be you, and you should press me if you don't understand it. So why is it that the alumina varies in this way? Why is it that the alumina content as we go up pressure in the plagioclase field, lherzolite field of pyroxene goes up, then why is it flat and why does it go down? And we'll see once we understand that, we'll understand trivially why FO2 does what it does. In the plagioclase field, as we go up pressure, the following reaction takes place. Olivine plus plagioclase goes to magnesium churmax, an aluminous pyroxene component, plus diopside. There's a lot more going on, but this is dominantly what's going on. And so as you have this reaction go to the right, as you go up pressure, you generate more and more aluminum pyroxene component, and that's why the aluminum goes up. The magnesium, this reaction goes to the right, I generate an aluminous pyroxene component, so it just keeps going up until I have exhausted my forced right, my anthracite, and there I am, I've progressively increased the aluminum content of pyroxene. What in the world does this have to do with FO2? Well, a characteristic of these models is that, and although they differ in detail, they have different amounts of spinel, they have different partitioning of iron 3+ and 2+ between the pyroxenes and the spinel and between the two pyroxenes. Nonetheless, a fundamental characteristic is that most of the Fe3+ is in the pyroxene. Now, this was anticipated with people like Hugh O'Neill, because he was measuring high Fe3+ contents in the pyroxenes. I'm not sure it's really sunk into most people, but most in these models, and to some degree in the measurements that have been done on natural peridotites, most of the Fe3+ is in the pyroxene. So what happens? As I react olivine plus anthracite to make pyroxene, what's the Fe3+ over Fe total ratio? What's the concentration of Fe3+? Number of grams of Fe3+ or moles of Fe3+ per total moles. Well, most of the iron 3+ is in the pyroxene. So the numerator, as we go up pressure, the amount of Fe3+ in the pyroxene doesn't change. It's all in the pyroxene to begin with. However, the total number of moles of pyroxene increase. So we've got constant Fe3+, because nearly all the Fe3+ is in the pyroxene, over an increasing amount of pyroxene. So the concentration of Fe3+, the mole fraction of Fe3+, which is closely related to the activity of Fe3+, which winds up being a good proxy for FO2, because we have a reaction FeO plus a half O2 goes to FeO 1.5, or if you want, you can make it Fe2O3. So the reason the FO2 goes down is it's driven by the same reaction that makes the aluminum go up. This increasing aluminum increases the amount of pyroxene, so iron is diluted. It is not iron 3+ diluted. It's not iron 3+ going from one phase to another. It is iron 3+ staying in the same phase, but this reaction decreases the amount of that phase. We can see this in the output of the models. If we look down here, this is the phase proportion. As you cross the plagioclase lherzolite field, the olivine goes down, the plagioclase goes down until the plagioclase is gone. The CPX concentration, the mass fraction of CPX doubles. The amount of OPX goes up by a lot. If all the iron 3+ is in the pyroxene and I've increased the amount of pyroxene by that much, the concentration goes down, and that's why the FO2 is driven down. The concentration of Fe3+ goes down by dilution. How about in the spinel lherzolite field? Well, in the spinel lherzolite field, here's a reaction that controls it. Now, if this reaction did proceed to the right, what would happen is that with increasing pressure, what would happen is that the amount of alumina in the pyroxene would go down because we would be reacting away the magnesium termac and making enstatite. So you might see a variation in alumina in the pyroxene, but if you did, even if you did see a variation in alumina, notice for every pyroxene you consume, you make a pyroxene molecule. And therefore, again, most of the iron 3+ is in the pyroxene, but the amount of pyroxene doesn't change as I cross the spinel field, even if there is a volume change. So the Fe3+ in the pyroxene over the total amount of pyroxene remains roughly constant. So the FO2, which is easily related to the concentration of Fe3+ in the pyroxene, doesn't change. Now it turns out that the amount of the volume change of this is the standard state volume change is very small, and so you don't get much reaction anyway. So, but even if you did, you would not change the FO2. And we can see that in the output here. The amount of all the phases remain constant. The reaction doesn't proceed, and therefore FO2, which has gone down from 1 atmosphere to about 10 kilobars, doesn't change practically at all. It just stays low. The FO2 goes down, it stays low, and then goes up. Okay, and you can see here the Fe3+ concentration is going down in the plagioclase field. It remains constant in the spinel lherzolite field. And how about in the garnet? Well, the dominant reaction controlling the alumina isoplus is magnesium termax again, plus enstatite makes pyro. So as I cross the garnet field, I am consuming pyroxene and making pyro. Now, initially, all the iron is in the pyroxene. Eventually, the garnet catches up. So, but what happens as you first cross into the boundary, into the garnet field, is constant amount of Fe3+ in the pyroxene. All right, but I consume pyroxene as I move to the right. So the denominator gets lower, and the concentration of Fe3+ in the pyroxene goes up, and therefore the activity goes up, and therefore the FO2 goes up. So this is, again, dilution, but anti-dilution. Okay, we're taking away the amount, we're concentrating the same amount of Fe3+ in less and less and less pyroxene. And you can see that here. The amounts of phases, the garnet, the olivine goes up, the garnet goes up, but the pyroxene amount of pyroxene goes down dramatically again. And so that leads to initially an increase in the amount of Fe3+. Eventually the andradite component or the skyagite component pops in and causes that maximum. But initially, you start with a low concentration of Fe3+, and the approximation that most of the Fe3+ is in the pyroxene is right again. And so, and that's responsible, again, this concentration of Fe3+ in the pyroxene, because the total amount of pyroxene goes down, leads to this increase in in FO2. Okay, now it makes an interesting prediction, and that is we have fertile peridotites. They have high alumina. As you extract melts from them, the alumina goes down because you've taken out basaltic melts. So this effect will go to zero as you have highly depleted peridotites. And we checked this. I mean, if we're right, it has to be right, and it is right. We've done calculations where we looked at a peridotite that instead of having 4% alumina, which is what you had in DMM, it's only got 1.4, and the size of the amount of decrease and increase in FO2 as you decrease crossing the plagioclase lherzolite field, increase going across the garnet lherzolite field, is about 50% of what it is in the fertile. I'm going to stop with this slide because I want a little time left over. We started about 5 after, but it'll give us 10 minutes for questions. Let's put it all together. So what we've been looking at is up here, okay? And I've put it back to relative to QFM because it's sort of hard to know what to do up here when I explain it, you'll see, but also this is what everybody's used to looking at. And here are the changes we see in our models. Here's that maximum. Now, as we go to higher pressure beyond 40 kilobars, it's well known that the FO2 relative to QFM goes down continuously. But there are phase changes that also influence this. One is you start to transfer pyroxene into the garnet phase. Well, by this point, most of the iron 3+ is in the garnet. So now you have dilution of the Fe3+ in the garnet by dissolution of the pyroxene component, which didn't have much Fe3+, and that contributes to a decrease. Down here, and this is something that Hugh said back in, I think, the early 90s, it was very similar to the argument we have here, and that is that Fe3+, when you, just before you reach the transition zone, Fe3+ is essentially entirely in the garnet. But then once you start to grow ringwoodite and wadsleyite, you start to transfer some of the Fe3+. You basically are transferring some of the Fe3+ into these other phases, thereby decreasing the Fe3+ concentration in the garnet, leading to a decrease in FO2. There is something that I just want to, I will finish up with here that is misleading in this. So this just puts it in context. What we're looking at is some wiggles, but these wiggles matter for magmagenesis and what we see in most peridotites. The FO2 is going down a lot here, all right? And relative to QFM. And so the people who work in the business, I've concluded, know exactly what they're doing, not surprisingly. They say that it is becoming more reduced, or the FO2 is going down relative to QFM. But people not in the field think that the FO2 is actually going down. Let me go all the way back here. And we go and look at this here. The FO2 with increasing pressure is going up, okay? And I've done the calculations up to 70 kilobars. I'm not confident doing it beyond there. And the FO2 continues to go up. So the absolute FO2 is going up, but that relative to QFM or relative to iron woodstite, most people were very interested in the iron woodstite because if it decreases relative to iron woodstite, you have a chance of precipitating metallic phase. But you mustn't fall in the trap when you're using delta FMQ of thinking you know what the actual FO2 is doing. As long as that absolute FO2 is going up with increasing pressure, this is a thought experiment which I think has no geological significance, but it's very important, I think, conceptually, because the actual absolute FO2 is going up with increasing pressure. If I took a peridotite at 40 kilobars and put it, and now I put a wall in. This is an artifice that people in thermodynamics use. Put a wall in that's rigid. It can support the pressure difference between 40 kilobars and 10 kilobars, okay? But it's permeable with oxygen. The higher pressure one has a higher chemical potential of oxygen. Oxygen will flow from the high pressure peridotite through the permeable, semi-permeable barrier into the lower pressure peridotite, even though, or make it 70 kilobars, even though the FO2, the delta QFM is lower. So you want to be very careful in all of this. But what this shows you is that this kind of phase equilibrium control has been suggested previously with the very same kind of argument, although it's not in the pyroxene anymore. Here it's mostly in the garnet. And you get big variations that reflect these things. So I'll stop there. I'm not going to talk about melts because I ran out of time. But thank you very much. I'm a little worried there are no questions, but let's see if there are any at the end here. Okay? Thank you.
Thanks, Ed. So if any of the audience want to ask questions, fire away.
Well, all right.
I think there was a question in the chat earlier, but then you addressed the topic. It was on the FMTO.
Yeah, I think his mic is off. Hugh, surely you've got a question here.
Don't put him on the spot. That's okay.
I'll say hi, Ed.
How are you?
Yeah, no, I think that that's a marvelous exposition of what happens with the change of oxygen fugacity in the mantle. But from my point of view, I think it emphasizes that the important thing is not what the chemical potential of oxygen, i.e. the oxygen fugacity is, but the iron 3 to iron 2 plus ratio. And you know,
we've only done this at one iron 2 plus 3 plus, and it will vary a lot. And of course, as you deplete the peridotites, they will also change in Fe3 plus 2 plus and go down.
Yeah.
But I only bring up the absolute chemical potential part because, you know, you never misspoke, but everybody else that comes after you does misspeak, and they say the mantle is reduced. The mantle is reduced relative to the shallow mantle. And it, by the way, we do actually see a decrease in the absolute FO2 in the plagioclase lherzolite field. That dilution effect is so great that you actually have the chemical potential of oxygen going down over the plagioclase field. I should say that one of the things that's very important here that you can comment on is, again, these trends are strongly dependent, really strongly dependent on the output of these models that say most of the Fe3 plus is in the pyroxene under these conditions. If that were wrong, you could change it. And in fact, when we first came out with this, people said, you know, I know you're wrong because Bauhaus and Frost showed that the FO2 went down when you went for spinel to garnet lherzolite. And it's because they assumed the garnet, at the garnet spinel transition, had much, much more Fe3. It goes up a lot. But at the first point of reaction, it is low. And so this fact that it goes up in the garnet field is entirely dependent on having the this concentration of Fe3 plus in the pyroxene right. And I assume people are working on it.
Which illustrates how important the activity composition models are for the Fe3 plus components in the pyroxenes.
Yeah, and while you have done such a good job with the skygite and the garnets, I'm not so confident with the pyroxenes, to be honest. But
no, no. Look, I think we've got a lot to learn there, and also the other conspicuous thing that's missing from these models is the very large effect that chromium has on alumina in pyroxenes, and this carries through then to what the effect is on the Fe3 plus components. Chromium only goes into the octahedral side of the pyroxenes, and therefore it grabs, if you like, available tetrahedral alumina that can no longer be used to charge balance octahedral iron 3 plus. And if anyone understood that, I'm sorry.
No, I understood it, and I you know, but I think that the melts has none of that in it. All right, because it doesn't put any chromium in pyroxene at all. But at least the Holland and Powell model, the Jennings and Holland version of it, they at least have chromium in the garnet and in the pyroxene, and melts. And what's amazing to me is that you're saying maybe it's very important, and you may be right, but one of these things doesn't even make an attempt with the Fe3 plus or the chromium in the garnet. And yet the results are so very similar. They're diverging at high pressure, by the way, but it is because melts doesn't have the Fe3 plus. But you know, it is all dependent on the quality of these models. And and they both incorporate. They are very different, by the way, in their Fe3+ in the pyroxene. They disagree whether it's concentrated inclined pyroxene versus orthopyroxene, and the concentrations are different, and yet they agree substantially on this behavior. So I think it's probably robust unless somebody were to throw out all the information, again, that you were partly responsible for, on the fact that natural peridotites have a fair amount of Fe3+ in the pyroxenes. I mean, you did a mass balance on the amount in spinel and pyroxene, and you know, 50–60% of it was in the pyroxene. I've forgotten the numbers. You may remember, but
Yeah.
you know, most of us would have thought before any of that work was done that the spinel contained all the Fe3+. I don't know, but it's dominated by the amount that's in pyroxene and the naturals. Now that may be that they're at low temperature, though. You know, they've equilibrated to low temperature, but nonetheless.
So in the chat, Mark Norman had a question for you. So it says, does the higher FO2 of Hawaii relative to MOB just mirror the greater proportion of garnet in the source? Or is there some other source effect, maybe intrinsic Fe2+/3+?
No, I don't know. There's also controversy over what the FO2 in Hawaii is. It's been generated by Nash and Wood, and I forget who the third author was. I think most people believe, and somebody, you know, can tell me if they think I'm wrong, that Hawaii, you know, the ocean island basalts, their sources are thought to have contributions from, crustal contributions from subduction. And so they think that you're looking at a variation in the bulk composition of the source due to a subductive component. What we have said, and again in this one paper that we've written on this, is, you know, you can't explain everything with this, but this effect is almost certainly going on, particularly in fertile sources. And it will be these other effects of metasomatism and so forth, unless they're so substantial as to overwhelm it, will be superimposed on top of it. But I think it's quite possible that you could arrange, as Marcus said, that you could assert and then explore the possibilities that the two things. One is there's more garnet in their sources, and secondly, they're at higher pressure, and so there's more garnet for that reason as well. And that you know, it's only an order of magnitude or so more oxidizing than Morbs. And so you could explain it in this way, but you'd have to look for some tests that were robust to rule out other possibilities. There's also, I think there is uncertainty because, you know, nearly all of the measurements on Hawaii have been on degassed magmas. And if they're degassed, they tend to be reduced on degassing. And so you have to remove the effects of degassing to get an estimate of the initial FO2. And that we've tried to do that in the only other paper I've written on FO2, but it is an insecure calculation because you have to know more than we do currently know about the effects of degassing on FO2. And also you have to think you know the original volatile content of the Hawaiian magmas because you have to know how much is degassed. And so anyway, it's a good idea, Mark. I would say that.
Penny, do you want to ask your question?
Yep, I had, that was a really interesting talk, Ed. Thanks so much. I had a question that was sort of along the same lines as Hugh and then another one. So titanium, I noticed that it was in the MELTS model, but not the Perple X model. So that would suggest it's not having a huge effect. But on the other hand, you know, there are these mantle peridotites with lots of ilmenite, titanium, amphibole, titanium phlogopite. But what do you think's going on in those? And is the titanium then substituting into your pyroxene to vary the FO2 in those
Well,
anomalous sections of the mantle?
The parts of the mantle that were, and there, I think people there probably know much more about this, but you know, how the flog up with a marriage sequence and stuff like that. You know, those are metasomatic veins. So I don't think that, now that maybe you melt something that includes those plus a lot of mantle that hasn't been so affected in some mixture, but I think that, I'm sure titanium has an effect. Again, the fact that the P melts is not all that different from the Perple X, it only suggests it's not dominating.
Yeah.
And that's the challenge here, to understand what the artifacts are and what is important. There's no doubt, they may be both wrong, by the way, but there's no doubt in my mind that the reason for the changes is entirely this Fe3+ dilution or enrichment due to the reaction.
Yeah, sure.
But there will definitely be perturbations on top of it. There will be perturbations on top of it.
Yeah, and second order kinds of perturbations with something like that. Yeah. So I'd love to learn more about your melting and that stuff.
You said you
has said, please flip through the slides on melting, so they'll be recorded with the presentation. Great talk from Mark and from me.
You said you had a second question, one related to Hughes, and then another, or the titanium one was the second one.
Did you include monticelite?
No, I don't remember if these guys have a monticelite component. Is that what you asked, monticelite, calcium component?
Yeah.
I
mean, I think it's probably, again, that's probably a third order thing, not a second order thing.
Well, you know, the calcium is so low in the olivines.
Yeah.
You know, people do try to use the monticelite component of peridotites that lack OPX to get another FO2. You know, in other words, you know, if you want to measure it with olivine, pyroxene, and spinel, for example, you know, you're fine. But what if you don't have orthopyroxene? So then you can write a reaction among a monticelite component plus.
Yeah, I mean, it's mostly that component will then affect your plagioclase and garnet.
Yeah, it's such a small amount of calcium.
But it's so small. It is a third order effect.
Yeah, yeah. I would say that it, I bet that P melts has calcium in the olivine, if only because I'm pretty sure that Mark Hirschman's thesis was on, part of it was on adding minor elements to the olivine model. And I believe he included calcium he did manganese, maybe nickel, and possibly calcium, I forgot. But I would think that they would include it.
No, I mean, it's minor. It wouldn't do too much. Yeah. Okay, thanks.
Okay. All right. Well, thank you for your attention. If there's any other questions, I can answer them. I have